All right, so the thing that actually got me interested in math, I was okay calculating things, but it wasn't, my passion until I learned some of the history and some of the theory and really the more abstract ways of thinking about things. Sometimes then I kind of throw out there some history or some theory in hopes that it brings something into perspective for you. But I think radian measure is kind of an ideal time to bring some of that in because its existence and the degrees that you've been learning and the rest of your life and all of that is really related to the history of when they were trying to sort out things about math that we kind of take for granted right now. So first, I in the beginning, so back in time, there were a couple of things at different moments that they were trying to sort out. One of them was how to measure rotation, and one of them was the relationship between the diameter of a circle and the circumference of the circle. The rotation, they considered first the rotation of the Earth around the sun, and they believed at the time that there were 360 days in a year. So each day they decided would be, one 360th around. Let's call that a whatever they called it in whatever language. But that's what we call a degree. So a degree is what they would have thought is the amount that we rotate around the sun in one day. Of course, that's false. They were wrong. There are 365 and a quarter days in a year, but 360 is what they went with. So that was the original reasoning for that. The diameter of a circle to the circumference of a circle, there are two things you look at with a circle, right? There's the area and there's the circumference. But logically, and I'm projecting here, I don't actually know, I haven't studied whoever originally came up with pi, but if I were at the time trying to look at it, I would think to myself, well, if I have this circle, I don't have my own tablet, so I have to adjust here. If I have this circle, or egg, hello, come on, there we go. So if I have this circle, then measuring around it is one dimension. Measuring across it is one dimension. I'm just going to erase this and get a different color and start over because that looks crazy. How about pink? Okay. Try to get this tablet to work a little better for me. Still an egg. It seems that wherever I start on this tablet, it decides is the end of the world. So let me just kind of start in that corner and see. That's a terrible circle, but we're going to pretend it's a circle. So move your mind into the universe where that's a circle. So when I measure around it, then I have a one-dimensional measure. It's just one dimension because it's just going string around. I mean, obviously it's two dimensions or we couldn't see it, but, that's the best way we can kind of draw one dimension. And the measure around really is one. It has no thickness like my drawing. And then the diameter also is one dimension. So it ought to be that there's just a linear relationship between the two. I ought to be able to find some number that universally, when I multiply the diameter times that number, it yields the measure around the circle because they're just related by the single value diameter. Once you move into area, you're going to need to have some squaring because we have two dimensions, so we have to multiply in each side, but for the circumference, we just have one. So they went basically to locate the number. And what they found as they searched out this number is that it was irrational. So let me talk to you about irrational numbers. If I put a number line like this, and so you're used to this, there's 0, there's 1, there's 2, somewhere in here is, say, the square root of 2. Look, I'm at the end of the world again. Okay, it's about here, square root of 2. In reality, none of these numbers have any width on that line, right? So you can mark them with a pen, but that's not the reality. Your pen mark really covers infinitely many numbers. And we can get our hands on some irrational numbers, the square root of 2, the square root of 5, the cube root of 13, anything where we take a root and the result is not a fraction, then we end up with an irrational number. But we don't have names for many of them. And the truth is that if I took all the numbers on the real number line and I put them into a giant infinite bag and you reached in and you grabbed one, there's actually probability 0 that you would get a rational number. The measure of the irrational numbers on that line is the full measure of the line. Those rational ones are just dots. But almost everything is irrational. But we have names for almost none of them because they don't come up in kind of counting, multiplying, dividing, but they are the bulk of the numbers. Pi turned out to be irrational, and so it needed a name. So they gave it the Greek letter pi. So pi initially was existing because it was the circumference divided by the diameter. That's why it has a name. It did that job, so it needed a name. It didn't have one. It's not a pretty square root of something nice. It's just the circumference divided by the diameter. So this is why pi exists. So when we say, oh, if you take a circle, then diameter times pi is its circumference, that's not some kind of magic that happened on a pre-existing number. The number wouldn't have a name if it didn't do that. Oops. Okay, so that's where pi came from. And then we have these angle measures, and that's where they came from. The question of why do you still use degrees up until pre-calculus, I don't know the answer to that. I think it's crazy that they do that. But what happened then is when we got to calculus, calculus has a method by which you can sort of measure if I'm going around an angle, then the distance that I went around a circle, say of radius r. So calculus is all about motion. It's rates of change, it's volume being pumped into something. It's all about things changing over time and what happens to them. So one of the things it measures is, suppose that I'm moving rotationally over time, and let's say I have a compass, so this is at the end of it, okay? And it measures then the length of this as I go around. So here's the angle theta. The result of that is this measure times r. So when I use calculus to just kind of measure this, it says it ends up, how far did you go around? And it was times r kind of all along, okay? The r is a constant that drags along, but the theta is the result. So if I measure that around, then I'm doing some portion of the circumference. So imagine that I went all the way around. And imagine then that the radius was r. So here's a circle of radius r. That means the diameter is 2r, and the circumference is therefore 2r times pi. Okay? If I go all the way around with calculus and I measure all the way around, the result should be r times the amount I went around. If the amount I went around is 360, then I get 360r. Now you do have that unit degrees flying around that you'd have to deal with somehow, because I'm measuring obviously some units of linear measure. I'm not measuring angles. But having to deal with that is a mess, and the whole foundation of 360 degrees was invalid. So then what happens is we end up where we have r theta, in the case of all the way around, needs to equal to r pi. So I can cancel these r's, so I need 2 pi r to equal r theta, cancel the r's. 2 pi should be the measure of all the way around. And in radians, it is. The reason that this is called radians, because I'm sure you notice the relationship to radius. I'm making these crazy eggs because I'm trying to avoid that weird no man's land that the tablet keeps hitting. But so if here's my radius, and I go out here, and let's say I start right here, so start here, and I start going around and measuring, and I want to end up where this measure is also R. When I've done that, so if I go, just take a radius and go around, then the angle between where I started from and where I landed is 1 radian. So a radian is the amount of rotation it takes to go 1 radius worth around the edge of a circle. Okay, so that's what a radian is. That's why it's called radians. But it also makes all your favorite formulas from physics that used to be beatings, because you had to deal with these conversions and you always had a pi that you had to toss in there and a 180. What you were really doing all along was changing it to radians because they work nicely with the physics. So I'm going to call this video, that's kind of the introduction to what a radian is, I'm going to call this one done. And then I'm going to just make a different one on the start of calculating going from radians to degrees